We often view our world as the absolute peak of planetary success. Earth sits in a stable orbit with liquid water, a nitrogen-oxygen atmosphere, and a magnetic field that deflects solar winds. This bias heavily restricted astrobiology. We've spent most of our telescope time hunting exclusively for carbon copies of Earth, orbiting stars like our Sun. But astrobiologist Dirk Scholz-McCooch argues this approach is backward. From a planetary perspective, Earth has significant biological limitations. It is far from perfect. In October 2020, Scholz-McCooch and a team of researchers launched a study with a different objective. Instead of searching for an Earth replica, they began hunting for super-habitable planets, worlds with environments where life could evolve even faster, larger, and over a much longer period of time. They took the thousands of exoplanets we've discovered so far and ran them through a strict set of environmental criteria. Out of that massive pool, they filtered the chaos of the cosmos down to just 24 candidates. To find the most abundant life, we have to look past our own planet's specific parameters and identify where the conditions for biology are more stable. To understand what makes a planet super-habitable, we have to look at our Sun. It's a yellow dwarf star. Yellow dwarfs have a maximum lifespan of about 10 billion years. That sounds long, but complex life takes billions of years just to get started. By the time an ecosystem truly peaks, a star like ours is already nearing the end of its stable life. A more efficient host for life would be an orange dwarf. These stars are slightly cooler and less massive than the Sun, but burn their fuel at a much slower rate, living for anywhere from 20 to 50 billion years. This extension of time effectively doubles or triples the window for biology to experiment, adapt, and evolve without the threat of a dying host star. A long-living star is useless if the planet itself dies. This brings us to the second filter, physical mass. An exact Earth-sized planet actually fails this test. To qualify as super-habitable, a world needs to be roughly 1.5 to 2 times the mass of Earth. That extra mass generates stronger gravity, allowing the planet to hold down a much thicker, heavier atmosphere to shield it from the vacuum of space. Internally, that added bulk traps heat. A larger planet keeps its iron core molten for billions of years longer than Earth will. That churning liquid metal sustains a powerful magnetic field, which acts as a permanent shield against incoming space radiation. The baseline for a world optimized for life is specific: an ancient, slow-burning star paired with a massive, heavily shielded planet capable of maintaining its internal heat. The final requirement comes down to surface conditions. Believe it or not, Earth's average global temperature is actually too low to support maximum biodiversity. A world about 5 degrees Celsius warmer than our planet would be more efficient. When combined with wide, shallow oceans, this extra heat creates global tropical rainforest conditions, environments where life multiplies rapidly. When astrobiologists applied these specific rules, they found a handful of incredible candidates. One of them is the exoplanet KOI 5554.01, which maintains a stable surface temperature of around 27 degrees Celsius. Beyond its perfect temperature, researchers believe this planet features hyperactive tectonic plates. The constant shifting and fracturing of its crust drives an aggressive nitrogen cycle. Nitrogen is the chemical bedrock for amino acids, proteins, and DNA. A fast, continuous cycle of this element creates the raw material needed for rapid biological growth. Then there are candidates like LHS 1140b and Luton b. Data suggests these massive rocky worlds hide deep, planet-wide oceans directly beneath their crusts. Luton b ranks so high on the habitability scale that the METI organization specifically targeted this planet in 2017. They used massive radio dishes to beam scientific and musical messages straight towards its coordinates. With ideal temperatures, with hyperactive crusts, and massive water reserves, these 24 filtered worlds represent biological engines that appear far more efficient than Earth's ecosystem. We don't necessarily have to look dozens of light years away to find an environment built for this kind of potential. We actually have one in our immediate cosmic backyard. This is Callisto, Jupiter's second-largest moon. Astronomers looked at its dark, heavily cratered surface and wrote it off as a dead, inactive piece of rock. But modern surveys revealed something entirely different. Hidden beneath that battered ice crust is a massive, salty ocean, surrounded by a distinct, newly detected atmosphere. When you apply the criteria to this moon, the results are startling. With endless subsurface liquid water, manageable low gravity, and active atmospheric potential, Callisto is holding the exact raw ingredients astrobiologists have been hunting for. There is only one massive obstacle keeping this moon from flourishing: the intense, potentially sterilizing radiation constantly blasting out from Jupiter itself. This combination of low gravity and massive water reserves has led some researchers to suggest it as a primary candidate for deep space logistics. If shielding technology can eventually counter Jupiter's radiation, Callisto's resources could offer a more sustainable base for expansion than the drier surface of Mars. From distant K-Dwarf stars to the moons of our own gas giants, these findings suggest that the conditions for biological growth are not limited to the specific parameters of our home world. The universe appears to be populated with environments optimized for stability over tens of billions of years.